Okay, welcome everyone to homework set 12. We're just going to dive in with the first problem. Okay, we're working on 5.11-4. Okay, so you got a box beam of wood, and you're trying to find the maximum allowable shear force. Okay, so if we just look at the values that were given, we get all of this stuff right here. Okay, and now we're going to try and look at the formulas that we need. Okay, so formulas that we're going to need for this is our starting one. F is just equal to VQ over inertia, right? And then we're also given an S here, and we have to keep that in mind. So in the book, our S formula is 2F over F. Okay. So, solving for this, okay, we can first just knock off some of the easy stuff, right? We know we can solve for baby f, basically. That is equal to 2, and then that's 1,000 over S. And we're converting that to meters, and we get that, and I can plug this in my calculator real fast, and we get some wonderfully big number, 1,000. Okay, so from there, we're just gonna dive right in and say, okay, inertia, that formula is going to be base times height cubed over 12, because we're dealing with a square. Rectangle, you can find all these values for inertias in the back of your book. Okay, and then the only other thing that we need to figure out is Q, right? Q is a general formula of area above where you're looking at the shear, times Y bar, okay? And we're gonna talk about this a little bit more. The book, their explanation for Q is a bit hazy, so I'm gonna explain this formula because I like to use it a little bit more and it makes more sense than what they have in the book. Okay, so let's look at this. So Q is equal to area times Y bar, okay? So if I try and draw this, same thing right here, okay? So we have this. Now we have to look at, okay, where are we looking at the shear, okay? And where basically are we looking at? And we're looking at it right here, and it's symmetric. You would also technically be looking right there and right there. Because it's symmetric, you don't have to look. You just pick one, and I'm picking this top, guys. Okay, so we have the centroid of the object, right? And then we're looking at Q, and we want to find the shear here, right? That's where it's going to break. That's where they've nailed in there so that it holds together. But that's the part that's basically not, that's the part we need to worry about, right? Because we're looking for the maximum shear force. It's going to break there first. So that's our shear, okay? Later on, you guys are going to do some more stuff with that. But okay, so you have a shear point right there. So Q is the area above the shear point. So in this case, it's this whole area, okay? And then Y bar is you look at the centroid of that area, and you go from the centroid of that area to the centroid of your actual piece, okay? And that is Q. So if we try and write the problem out for this, right, Q is going to be equal to our, let's look at the area first. So it's the area of that shape is 0.26 because we're going in meters, times 0.025 meters. And then our Y bar is just going to be, right, we're going from there to there. So it's really just our 0.025 plus 0.26 over 2, right? And I believe that gets something like 0.1425. Okay, so then that is how you solve for the q. Okay, so going back to the problem, we have all these values. We're going to just start plugging into this original formula, right? Okay, so we want to solve for shear, so we can say shear is equal to that baby F times inertia over Q, right? I'm just going to create a new slide because it's starting to get a little messy here. So shear is equal to F over Q, right? Yeah. Okay, so we have that shear equation. We know how to solve for Q. Now the only thing is we have to look at I, remembering that I is just equal to our base times height cubed over 12. And we're looking at this whole structure, right? So this whole thing for our inertia. Okay, so that's going to be pretty straightforward. Because it has a hole in it, it's a bit, you have to do a little bit more. So if we look at this, we do the outside first, 0.26 by 0.31 cubed over 12. So this whole distance right here, right, that's the 0.31. And then we have to subtract the inside inertia, which is this guy. So that is going to be 0.16 times 0.21 cubed over 12. Okay, so that is our inertia. So if we take everything and we start plugging in values, right, we're going to get, let's see here, we're going to say our shear is equal to our force, and then if, okay, so if you calculate that, it's going to be the force times 0.4458. That's just solving using all the numbers we've gotten, and then that's just 24 times the 0.146, and then that's just going to get us our 10.7. And that 24 is kilonewtons, so it should be times 10 to the third as well. Okay, and that is how you find the shear in this problem.